Well, welcome. I'd like to introduce you to our compact, high-power, mid-wave infrared laser system. My name is Arturo Chavez. I'm from MP Photonics, and this is a Navy topic 221041. Let me tell you a little bit about our company, MP Photonics. We're based in Tucson, Arizona, and our business is related to fibers, fiber lasers, fiber amplifiers. We make our own glass and fiber in our facility in Tucson. It's indicated there on the left. You can see pieces of glass on the right, preform and a drawing tower. Um, and just to tell you a little bit more about our company, we were founded already in 1998, a spin-off from the University of Arizona College of Optical Science. And we've been working through SBIR and other programs to commercialize our technology. Now we have done that through patents. We have 37 issued patents in our glass and fiber areas, and we have now OEM customers in oil and gas sensing, in LiDAR, in metrology, in the new quantum computing areas, and in injection seating. These are all based on our glass and fiber uh, technology and platforms. So to specify a little bit more clearly the need here, the Navy has a challenge that can be met with this next generation infrared countermeasure system. And the goal is to protect Navy aviation and maritime assets from different types of adversarial threats. Current systems are using lasers, but these lasers are very costly and bulky, and they do produce the right wavelength of light, but in a very awkward and difficult way. So the next generation of these lasers need to operate over multiple wavelength bands and engage through the atmosphere directly. And of course, the benefit is that any incoming projectile or missile can be deviated from its path and save lives as well as any kind of assets that are being protected. So the important thing is that the system have a reduced swap, size, weight, and power, and that it can jam incoming missiles with its infrared beam. So the challenge, of course, also is that it has to work under all kinds of conditions, be reliable, and be effective in all of these campaigns. Now, the solution that we're proposing is based on the glass and fiber technology that MP Photonics has commercialized over all these years. And so we're developing a 100-watt mid-wave infrared laser that covers the relevant atmospheric bands of 3.5 to 4.1, as well as 4.6 to 4.9, using a mid-infrared fiber cascaded Raman laser. Now, the benefit of this type of approach is that it can be all fiber. That is, over time, has become the preferred platform technology for many lasers, including very high power lasers, because of its uh, ease of use, its scalability, its performance metrics, such as being very pure beams and high power. So all of these are beneficial from the point of view of our platform technology. And this particular laser makes use of a new glass and fiber, the Tellurite glass, which has been developed and patented by MP Photonics and has been supported by the Navy in multiple Phase 2s and SBIR programs. Overall, the advantage is clear that you will have a more reliable laser because there are no moving parts. Fiber lasers are spliced together. There's no alignment. It operates at room temperature. It can also have precise temporal control of the outgoing beam, pulse width, and repetition rate. It has an improved swap in terms of size, weight, and power and efficiency. And importantly, it can be portable, integratable into many Navy systems. The overall performance is summarized here. The operating bands of the operating wavelengths of this laser will be between 3 micron and 5 micron. It can reach high average powers of 100 watts, which is suitable for engagement distance in the application. It has a very pure single mode output beam, indicated by this metric of the m squared being less than 2. Very efficient in terms of electrical to power output, and it can be used in integrated into many different kinds of systems. Now, currently, we have been working on this program for some years. This is a kind of secondary phase 2 from one of the original ones, but we have continued our development of the fundamental fiber itself in terms of making it lower loss and higher power handling. And so we've also been able to demonstrate high power operation in our lab with good beam quality and with coverage so far up to about 4 micron. The 4.7 band is still under development, and as that is going forward, we will integrate a system into a prototype module for further testing. The key features, advantages, and benefits of this type of technology are summarized in this slide. The features, it's a fiber laser with all the good benefits of fiber laser technology, with a high power beam coming from a single aperture. So all the light comes from one place. That makes it easier to focus or collimate or manage in optical systems. It also, because of its single mode character, can have long distance engagement through the atmosphere. The fact that it can cover all these different wavelengths all at once means it's difficult to jam, difficult to filter or remove from the beam path. And so it makes it simpler to get to the target. And there's no need for complicated beam combinations from many different lasers to get the light to the target. The all-fiber construction results in improved swap and efficiency, and the underlying benefit is no moving parts, no exposure to environment, and ultimately a much better reliability. And it has some other feature, which is the temporal gating, which means you can actually encode some time signatures on the beam. This could be for identifying friendlies or other features which is not easily implemented in other technologies. So just a general overview comparison of how our technology compares to existing ones. This is just kind of showing what the existing Ti-Sapphire laser and its complicated structures of OPO, which is basically a benchtop a scientific research system. Very large. You can see a lot of alignment required, a lot of different stages, a lot of different optical elements. So in comparison from the size point of view, it's a fraction of the size. And although I don't show an internal design, the fiber laser is basically much easier to construct and to keep in operation because it's just the splicing of fiber across the system. The transition to fleet, of course, very important. We have a few different milestones for that. Making the prototype, reworking it as needed for the based on the test, and then final development, test, and evaluation. These are different phases of the next part of the work, but we're still in the prototype construction part of it. Organizations that may benefit from this technology in the Navy, we've identified here, IWS-2, but of course other branches can also benefit in terms of Army, Air Force, and the High Energy Laser Joint Technology Office. So it's a very general problem that is needed needs a solution, and as a platform technology, we feel we can uh, provide some solutions to many different uh, of these applications. Essentially, to get to the next step, since it is a complicated application, we are needing a partner. And our purpose in participating in this forum and in this program is to identify a suitable partner or partners that can help us integrate our laser into their systems. Um, uh, as a laser manufacturer, we feel very confident that we could make the laser that meets the requirement and deliver to the right prime or partner. But going from there, the integration into a real military system and the final testing and then taking it to the full transition needs a bigger organization with a lot more experience in that than we currently have. So that's where we think the next step for this progression is. I'm welcome your contacting me. We're very happy to work together in all different forms, both in terms of technology development, prototype development, integration into other systems. So you can reach me at these numbers. And in Tucson, Arizona is our base, but you can call or email me at your convenience. So thank you very much for your attention.